Good day. I am representing the Group 5 of the MS Modern Geometry class for the first semester of the academic year 2020-2021 of Central Mindanao University. So, welcome to the world of modern geometry. Now, I am with Roland James Cabarles and Miss Jody Ann Caspen. Of course, yours truly, I am Eleanor Jones Amy. Now, what to expect in this video? In this video, we will be proving the theorem number 22. We will be defining symmetry groups and we will be giving a brief background of the translations. Okay? So before anything else, let's have first a recall on the things that we have discussed last meeting with the previous groups. It is defined that the isometry or a mapping T of the Euclidean plane onto another Euclidean plane is said to be an isometry if for any x and y in the Euclidean plane it holds that the d of tx and ty is equal to the d of x and y. Alright, so as I've said a while back, we will be proving the theorem number 22, but we will have to stipulate first the stipulations, of course, of theorem number 22. We have here, if T and S are isometries, so is TS. If T is an isometry, so is the T inverse, and the identity map of the Euclidean plane is an isometry. Okay, we will be proving them one by one. First stipulation, if T and S are isometries, so is TS. Now here's the proof. If T and S are isometries, then for all x and y an element of the Euclidean plane, it holds that the d of tx and ty is equal to the d of x and y, and of course the d of sx and sy is equal to the d of x and y still. Alright, now the d of the t of s and x and t of s and y is equal to the d of s and x and s and y. By definition, this is equal to the distance of the ordered pair containing x and y. Therefore, TS is also an isometry. Alright? Now let's proceed to the second stipulation. If T is an isometry, so is T inverse. Here's the proof. If T is an isometry, again, then for all x and y an element of Euclidean plane, it holds that the distance of Tx and Ty is equal to the distance of the ordered pair containing x and y. Okay, let T inverse be the inversing mapping of T. Then for all x and y an element of the Euclidean plane, we have the T inverse of x equals Tx and the T inverse of y is equal to Ty. Then we have here the distance of T inverse x and T inverse y is equal to the distance of Tx and Ty, which is by definition, this is equal to distance of x and y. Therefore, T inverse is also an isometry. Alright? And the last one, the identity map of the Euclidean plane is an isometry. Here is the proof. If the identity is an identity map, then for all x and y an element of the Euclidean plane, it holds that the identity of x is equal to x and the identity of y is equal to y. Okay, hence, the d of ix and iy is equal to the distance of x and y. Therefore, in the identity is an isometry. Alright? Now let's proceed to the symmetry groups. Definition. Let F be a figure in the Euclidean plane, then the set L of F equals the set containing T, which is an element of I of the Euclidean plane, such that the T of F is equal to F, is a subgroup of I of the Euclidean plane called symmetry group of F. So here is the proof. To show, we have for all T and S here an element of LF. TS inverse is an element of LF. Here's the proof. TS is an element of LF. It implies that the T of F is equal to SF. Now, it implies then that the TS inverse of F is equal to S and S inverse of F. This implies then that the T of S inverse of F is equal to the I of F. And the T of S inverse of F is equal to F. Hence, T of S inverse is an element of LF. Therefore, LF is a subgroup of the IE square. Okay? So, in layman's term or as an illustration, a symmetry refers to the group of translations. Now, for example, here we have the equilateral triangle. So those broken lines that you can see on the equilateral triangle, those are the axes of symmetry. Axes because it's plural. Okay? We have here the PU, the line PU, the broken line PU, that is through flipping. And then flipping and rotation. And for isosceles triangle, we only have one axis of symmetry because we can only do the translation using flipping. Why? Because when we rotate that, that does not go back to its pre-image, which is the isosceles triangle. Okay? Now let's have the brief discussions of the translations because it will be further elaborated by the following group, which is the group 6. Now recall that in reflection, it is defined that for a line L, the reflection in L is the mapping omega sub L of the Euclidean plane to Euclidean plane defined by the omega sub L of x is equal to x minus 2 times the length of x minus p and n times n, where n is a unit normal to L and p is any point of L. Okay, now we have here a question. Is there a simple way to describe the product of two reflections? The product of two reflections depicts the translations, of course. So we have here omega sub m times omega sub nx is equal to omega sub m mx minus 2 times the length of omega sub mx minus p, I mean it's n. Omega sub nx minus p and n times n. So it gives you x minus p times the length of x minus q and n times n minus 2 times the length of x minus p and n times n plus 4 times the length of x minus qn times n and n and times n. Okay, this is somewhat, this is actually a composition of function. So we have here x minus 2 times the length of p minus q and n times n, and then it gives you that the omega sub m and omega sub n x is equal to x plus 2 times the length of p minus q. Okay, the last step uses the fact that pq is perpendicular to m. And of course, that concludes our discussion, our report. For your questions, please just reserve it during our virtual class. Once again, this is Elner Jones Inyo saying thank you for listening. Have a great day and God bless.